Now let's see. What are these two mutual recursions going to do? These two natural mutual recursions, what are they going to do? This will produce integer or false depending on whether it's found in first of LOE. Let's make that a little bit more compact. If n is found in first of LOE. And this second one will produce integer false if n is found in rest of LOE. Now if we find it in the first, there's no use looking in the rest. We're supposed to find one of them. We don't need to find more than one. So that suggests an if. Now what's the question? Well, this thing produces false if it can't find it. This natural mutual recursion produces false if it can't find it. So, and I apologize for the double negative here, but if it doesn't produce false, that means it found it in the first. So the way I'm going to phrase this question is not false that. And that will mean is it found in the first? Is it found in first LOE? And if it is found in first LOE, well then that's what we want. That value that came back, which is going to be an integer, is what we want. And if it isn't found in the first of the LOE, well then we better go look in the rest of the LOE. That's the natural recursion. Now let me just note this question here, which I phrased as not false, find dash dash element. I could also have phrased this question as open paren integer question mark, find dash dash element dash n first LOE. In other words, I could have used integer question mark instead of not false. And the reason I use not false is it's more general for backtracking functions. When we see other backtracking functions, we'll have this same not false pattern. So let's see, maybe, hopefully, I'm done, and I am. All the tests pass. Now, why is this called backtracking? Well, let's just step through a couple examples. Let's add one more example to this. We'll put it up here. Let's look in D6 for D6. Well, if we look at this tree, we start at D6 and we're looking for D6, and immediately we find it, so we're done. Now, here's another example. Let's look in D6. I'll add one more here. Let's look in D6 for F1. And whenever I add an example, I actually should run it, just to be sure it's working. And they are. Now let's look in D6 for F1. Well, what happens is we start at the top of the tree, we start at D6. It's not F1, so we go to the subs. We go to the first of the subs, which is D4. It's not F1, so we go to the subs. We go to the first of the subs, which is F1, and it is F1. So we found what we want, and we produce 1. But now let's look at what happens in this case, where we look in D6 for F3. Well, again, we start at D6. We haven't found F3. We go to D4. We haven't found F3. We go to F1. We haven't found F3. We go up to D4. Now we look at F2. We still haven't found F3. We go back to the next branch. So now we come down to D5. We still haven't found it. We go down to F3. We found it. And each time we get to a failing node with no sub-elements, those are called leaves because they have no branches anymore. Each time we get to a failing leaf and we go back up to its parent and then try the next child, the next sub, That's called backtracking. We back up to the previous branch and go down the next branch. And that's why this is called backtracking search, because it has this pattern of going all the way down to branches, looking for what we want, and anywhere we fail, we produce false to go back to the next branch, and then that goes to the next sub. Okay? And this if not false of looking in the first branch pattern is emblematic of backtracking search. And as I said, we'll see more backtracking search examples later in the course.